Okay, thank you very much. Good morning, everyone. Thanks for your kind introduction, Ruth. I'm going to share my screen. Let me see. Okay, I hope you can see my screen. Can you?
Yes.
Yes. Okay. So, yes, the title of this presentation is How many types of energy consumers are there in Europe? And there are a lot of things to say, so let's start. So, why determining the types of energy consumers that exist in Europe is relevant? So, because in many applications, knowing the proper residential electric load profile is a key factor. To illustrate this, we will start talking about the energy system models. Energy system models are tools that help energy analysts to evaluate the impacts of long-term scenarios. So ESMs are quite good on the supply side, but they lack the degree of accuracy required on the demand side, especially when we talk about households. So this happens because the behavior of the households are very irregular when compared one to another. And the pre-established profiles that are used by the energy system models have problems to capture all these possible cases. Other examples where knowing the proper load profile is relevant are, for example, when we want to find the optimal size of a photovoltaic system for a house, or to evaluate the performance of an energy management system, or even to design electricity tariffs. So in these examples, using the wrong residential load profile may bias our results. So in this work, the objectives are the following. First, obtain a set of profiles that define the electrical behavior of households. Second, create a household persona for each of those profiles. A persona is a description of the typical household behind these profiles. And just with these 2 points alone, we would be able to accomplish the title of this presentation. That is that we will be able to determine the types of energy consumers that there are in Europe. In addition, we will go beyond, and we will also evaluate how these profiles are distributed among the regions or countries in this case, and study their differences. And finally, we are going to evaluate also the distribution of the profiles over time, in particular regarding how the COVID pandemic lockdowns have affected the household behavior. So at this point, is also convenient to see how this work can help achieve a state of net zero carbon dioxide emissions. So understanding the composition of the electricity demand at the household level will allow us to first segment the market. That is, it will be possible to know in advance for which sector a given technology will be most profitable. In addition, energy analysts and policymakers will be able to better define their interventions to promote energy efficiency, demand response actions, and encourage policies that foster investments towards the energy transition. And therefore, understanding how the household electricity demand is articulated also contributes to achieving the carbon neutrality goals in the European Union. So, to achieve all these objectives that I've been talking, we have followed the methodology that I'm going to explain in the following slides. So, that methodology is summarized in this figure. So first, we have a large set of thousands of dwellings, as you can see here. Each one is generating a load profile, those ones here. The differences between the load profiles that you can see here are due to a large number of factors, such as, for example, the size and type of the dwellings, the socioeconomic conditions, the consumption habits of the people inhabiting the dwellings, and so on. So these load profiles are made up of thousands of samples, and they may have different lengths. So it's necessary to find a way to work with them in an efficient way. So to achieve this, we will use a dimensionality reduction technique known as feature extraction. Feature extraction, which is illustrated here with those numbers here, computes a set of values for each load profile. As you can see here, for a given load profile, we get a number of values. These values or features represent certain characteristics of the load profiles. So by reducing the load profiles to a small set of relevant features, all the analysis that we have to do later will be computationally less complex. So in particular, we have computed over 3,000 different features for each load profile, and we have selected those features that perform the best. We will see it later. Finally, to build the set of profiles of electrical behavior, some unsupervised classification techniques, in particular the clustering analysis, have been applied to the features. So this has led us to obtain 40 different electricity consumption patterns, like this one, or personas, if you want to call it, that we have represented for better visualization as heat maps, as you can see here. So the load profiles with which we have worked come from a bunch of different sources, okay? Most of them are public, but there are also private. In total, we have gathered 25 data sets with different sizes, formats, and characteristics, okay? And we could incorporate some more of those data sets if we find them, okay? So the number of load profiles of each data set, as you can see here, is variable, and they range in that case from thousands to just a few tens, okay? Since each dataset requires a different pre-processing, I mean, because of this, the different datasets require different pre-processing. Okay, because of that, we have prioritized, prioritized in our preliminary analysis those datasets with the highest number of time series, which are those in purples. The ones that appear in white, among the purple ones, we incorporated them later. So when our preliminary analyses were quite advanced. So that's why we didn't include them in the preliminary analysis. So all the analyses presented in this work have been performed with those 5 datasets that appear here in purple. So one of the aspects that first called our attention when saw all the datasets is the fact that the vast majority of the datasets are originary from the UK, as you can see here, or from Australia, Ireland, and other culturally similar countries, such as New Zealand. We have also another from Canada. So the dataset selection has to be done in a geographically diverse way to avoid possible biases. Okay. Of all the datasets, we discarded those with very short time series, or those that only include data on appliances, like those ones with some metering written on them, and those that are not complete households. There's those that are, those that are in red has been discarded. Some of the datasets, the ones in blue, have very recent data, and we will analyze energy consumption before and during COVID lockdowns in a future work. This is something that we have performed already in the dataset of Guyana, and we are going to talk about it. In total, we have used for our analysis nearly 24,000 load profiles from 6 datasets and representing households from 5 different countries. So datasets require certain cleaning before they can be used for analysis. So apart from the conversion of the raw data into independent files or timestamp values separated by commas, it's necessary to fill in the missing data. So depending on the length of the gaps, imputation has been performed just by using simple interpolation algorithms, if the gaps are short, or by using the last observation carried forward method, which takes data from the previous week if the gaps are longer. Okay, another thing to deal with is the management of time. We want all time series to be referenced to their local time, regardless of their original time zone. So we had to remove the 1 hour discontinuities produced by the daylight saving time, the summer time, in spring and autumn. In addition, we wanted all the seasons to be aligned in all time series. So we have moved the time forward by 6 months in the case of the data sets from the Southern Hemisphere, the ones of Australia and New Zealand. We have created also different data sets to separate the distortions created by the lockdowns due to COVID-19. Okay, so we have done this so that they don't impact on the previous time series, and the differences can be cross-checked in a later step. Moreover, we have only worked with time series of only one complete year in duration or longer, and we have excluded those where all values are 0. This only happens very rarely, but this is some processing that we have to do. And here in the image from below, we can see an example of what a time series looks like in blue for several days. Okay, so as for feature extraction, we have computed more than 3,000 features for each time series. The features computed include basic statistics, which include statistical moments such as the mean, the variance, even quantiles and quartiles, and statistics related to outliers. Seasonal aggregates, these features are obtained by splitting the time series into subsets and then calculating statistics for each subset. Those subsets correspond to different time bands and comprises all samples of the time series for which their date and time fall within its particular time band. For example, the subset 4 to 7 in summer includes all the samples of the time series for which their time is 4, 5, 6, 7, and their date is in summer. Okay, so the statistics computed for each subset are the mean, the standard deviation, and also the sum. Using the same times as before, we have also identified the ones containing the maximum and the minimum values. That's the peak time bands. We have also computed the autocorrelations, electric load factors for selected periods of time. And also we have computed predefined features computed by certain packages of the R programming languages, such as, for example, TS features and Catch-22, that we will talk about it later. So for our analysis, we have only selected, or we have created just 5 subsets of features. We have 3,000 of features computed for each of the time series, but we have only selected 5 subsets of a reduced number of features. So the first subset is what we have called the seasonal aggregates again. So the features that we have included in this group are the mean energy consumption at 6 specific periods of 4 hours of the day and per season of the year for the entire time series. So we have also added, so yeah, this is here. And apart from this one, we have also included an extra set of periods which are related to the current Spanish electrical tariff. This one counts as another subset of features. So the third one would be this, the one containing 5 peaks and off-peaks of mean energy consumption. We have included the off-peaks and a similar indicator for weekdays and weekends. I mean, so those 5 features are used as the third set of features. So the fourth subset of features accounts for measures of seasonal strengths and autocorrelations. And the last subset is known as the Catch-22, and it's well known in the literature because it contains 22 selected features that show a good classification performance regardless of the type of the time series. So after inspecting our preliminary results, we found that the best subset of features is the first one, the one of the 25 seasonal aggregates by 4-hour periods and season. Okay, so this will be the one that we will use in our subsequent analysis. So to segment the time series according to their features, we have tested 9 clustering methods, including the hierarchical methods, such as the agglomerative, nesting, and the divisive analysis, partitional methods, such as k-means, partitional aromodioids, Clara, fuzzy analysis, methods based on artificial neural networks, such as the self-organizing maps and the self-organizing trees, and also model-based clustering. Eventually, after inspecting our preliminary results, we found that the clustering methods that work the best for our datasets are k-means and the self-organizing maps. So to help determine the optimal number of clusters, we computed a series of cluster validation measures. These measures help assess the quality of a given cluster analysis. The validation measures can be classified into 2 large groups, which are the internal, containing the connectivity, silhouette width, and tan index, and the external, containing those 4 Q. We have computed all 7 types. The resulting curves constructed from the cluster validation measures have been used to help decide the number of clusters as a support to the qualitative validation provided by the domain experts consulted. So based on the prior knowledge and the expectation on the number of clusters that we had, and supported by the fact that the validation measures are relatively similar at those ranges of interest, we have selected the number of 40 clusters for our analysis. So once the resulting clusters are known, it will be really useful to visualize their contents in a way that facilitates the next analysis. So the content of a cluster can be represented as the average of all the time series that compose that cluster. So to represent the clusters, we have used heat maps. Heat maps are just 2-dimensional grids that show with different color intensities the variations of the electricity consumption. So the grid that we have used is more or less like this one. The horizontal axis of the heat maps have been set to represent the days of the year, while the vertical axis represents the hours of the day. Okay, in this way, the average electricity consumption for a whole year can be observed at a glance. So the computation of the average time series of a cluster is based on the week date representation, which is described in the international standard for the weeks. Okay, so given a particular sample of the time series for a particular date and the time, it can be arranged in this grid by computing the week number, the W, and the D, which is the weekday number of the day. Okay, so you see that, I mean, we have 371 days in that standardized year. So its date will have its week number and its weekday. So by introducing those values in that equation here, we will get the column, the exact column in which we have to place that sum. So why are we doing this? Because, I mean, because the samples with the same day and month, but from different years, are placed in columns that will be near each to other. And at the same time, they will be respecting the day of the week. So keeping the original day of the week of each sample of the time series is really important for our analysis, because the differences in electricity consumption between weekdays and weekends will be highlighted. So the statistical measure used to compute those matrix averages is the median. We have checked that using, for example, the mean instead of the median over-represents the outliers of some time series, and the result that we obtain is excessively biased. So we have preferred to compute it using the median. In addition, other heat maps with other measures have been obtained, such as, for example, the mean absolute deviation, which is an analog of the standard deviation for the mean, for the median, and the relative mean absolute deviation here, which is an analog of the coefficient of variation when we are computing the mean. So this one, broadly speaking, allows us to see where the variations of the different time series are more intense. From now on, we will show only the medians because I think that they are self-explanatory and they allow us to understand perfectly the patterns of each one of the heat maps. So we can start with the persona descriptions. So to analyze in detail the 40 electricity consumption profiles that we have obtained, we have developed a taxonomy and a decision tree, which are based on the similarity of the electricity consumption behind each profile. So on the one hand, we contacted two professionals with expertise in the electricity system so that they developed a taxonomy based on their expert knowledge. And on the other hand, we also generated automatically a hierarchy by using a dendrogram that we have obtained by hierarchical clustering. So the automatic taxonomy is shown here in the form of a dendrogram, which are those species of branches of a tree. And the one taxonomy developed by experts is shown with different colors. So the two resulting taxonomies turned out to be quite similar, because I mean, we can see that different colors are hanging from common branches. So this indicates that the taxonomy generated by the experts doesn't differ too much from the taxonomy generated automatically. So we find 5 well differentiated groups of consumers. On the one hand, the largest group, which is here in orange, contains almost 3/4 of the load profiles analyzed, and is formed by named regular households, the primary residents that it's written here. On the other hand, we have a group formed by secondary residencies, which are those residencies that are not only used during the summer holidays, that are used during summer holidays, which are represented here in blue, that corner of the dendrogram. There's another group where consumption is more associated with equipment, which is in purple here, such as, for example, energy storage or electric heating. We have also a group of offices and small businesses, which are in green. In this case, it has been split into 2 different branches. And finally, the tiny group, which is consumption associated to street lighting. Okay, so if we zoom in on the largest group, which is the one of the primary residences, we can get a subdivision according to behavior. So we have a large group of households, which are the 30% of the total, in which the behavior changes during weekends, which appear here in green. Then we have households that spend all day in home, which appears here in purple. Then also households that make more electrical consumption at midday, perhaps because they are using electric kitchens, which are pointed here in yellow or orange. And the households where we have also a group of households where we find more pronounced consumptions around all meal times, which are those in red. So if we have a look to the clusters, we can even go with more detail in the classification. We see, for example, here that they depend on two main variables. The first one would be if the behavior changes during the weekends or not, as we can see here. I mean, for example, in this group of 4 clusters, we see that the behavior changes during weekends because we can see several vertical stripes with different intensities to the rest of the color. So the stripes are the weekends, while the other band represents the weekdays. So we can see that there are certain differences between the consumption in weekends and weekdays. And also, apart from if the behavior changes or not during weekends, we see that another interesting variable is the kind of meals that they take during the day when they are at home. For example, in the first one, we see that people is not at home during the day, but they arrive at night and they do the consumption there. This one, for example, is going home to have lunch and also the dinner. In this one here, we see breakfast, lunch, and also dinner. And in this here, we see an intense breakfast, but just but not lunch at all. But also we see a dinner. So the meal times are also can be used to read that classification of the pattern of consumption. So we are going forward. We are going to explain a bit the secondary residences. We see here 2 examples. We see, for example, this one on the right. We see that this consumption happens only during summer, in summer. So we see that it's more intense during the day, probably because they are activating the conditioned air or something like this. And also we see this pattern, this example, in which the consumption is intense in summer, but also during certain weekends and certain holidays, such as Easter or Christmas, these kind of things. So this is telling us that they are secondary residences. We have the houses with high consumption. They can be divided into 2 groups. Those using, for example, electricity heating. That would be this one. Probably they are using electric heating, and it is consuming a lot compared to the rest of the consumption throughout the year. And also there are some households or residences that are using thermal energy storage, which has that pattern in which we see high consumptions at those peaks of the day during the winter. For example, in that case, is during the winter seasons. Then another group would be the patterns associated with offices and businesses. We here can clearly see the schedule of the open hours of that office or business. We see that they are not working during weekends, not even during holidays, and they are working, and the consumption is more intense during the office schedule. Okay, and the last pattern that we see is this one, where the consumption is complementary to the solar lighting pattern. So we determine that they belong to street lighting. So we can see some street lighting associated patterns where energy consumption is activated complementary to the solar patterns. So we are starting with this. We have commented all the pattern obtention and all the taxonomy would be complete. So now we'll go to explain a bit about the regional distribution. Okay, so regarding regional distributions, our analysis here provides the following highlights. So here we have represented the clusters with more than the 5% of the time series for each one of the countries that we have computed. And we can see some things that may call our attention. I have written here, but I think that it's better that I tell you as we explain in this slide. For example, the first thing that we check is that there are two clusters which are among the most prevalent in all the regions except in Ireland. These are the patterns numbered as 15 and 28. So these consumption patterns are associated with regular behavior of people which stay at home during all the day. But the main differences between 15 and 28 is that 15 has less consumption in summer and 22 shows no change in summer. So the second thing to highlight, for example, in this regional comparison, is that the Ireland dataset, the Irish dataset, is the one that shows the greatest differences with respect to the rest, although it shares many characteristics with other countries analyzed in the Anglo-Saxon countries, basically with the UK and the US. Okay, and the third conclusion that we can draw here is that the Portugal and the US share a pattern that clearly dominates the dataset. This is the pattern 36, which we can see here in pink, intense pink. And this pattern contains the small and medium-sized companies that do not close for holidays and open from 6 a.m. In particular, the five most popular clusters comprise more than the 90% of the time series in Portugal and in the US datasets. In the rest of the datasets, those clusters just comprise the 60% of the time series. So this analysis has some limitations. The main limitations of the analysis are, for example, first, we are lacking random sampling. So the results that we get here must be taken with care. Second limitation is that we also lack data that provides some context. So it's not easy to stratify further and correct for potential biases in order to extrapolate. And another limitation is that it's important to remark that we are analyzing some datasets with small amounts of load profiles, of which we really don't know their origin, as is in the case of the Portuguese and a bit less in the US datasets. Okay. So finally, we go with the analysis of the time series over time. So this is the final analysis that I'm going to explain in that presentation. So here, what we are going to analyze is the impact that the COVID-19 pandemic has had on energy consumption habits. So the objective of this assessment is to detect the changes in behavior of the patterns. So to do so, we have split the load profiles provided by the Spanish Goyener dataset into two sub-datasets, and we have clustered them independently later. So the first sub-dataset is the pre-COVID-19 dataset. This dataset sets the cut-off date at 1st of March. Since the lockdowns in Spain started on March 14, 2020. The second dataset then is the post-COVID dataset, and all the time series start at 1st of March, and they comprise at least 1 year of data, but forward. Okay. Once we have the dataset separated, what we have done has been to compute 20 clusters per dataset and perform a mapping process of the pre and post COVID datasets using our previously computed 40 clusters as a connection. So probably this will get more clear in the following slide. So as I said, each of the 20 newly computed clusters of the pre and post COVID datasets have been linked to one of the top 40 clusters that we saw before. So we have used a semi-automatic approach using Euclidean distances between the clusters, and we have choose the nearest one that matches. So all the automatically matched pairs have been manually validated after that, since in some cases cluster distances were very similar, such as you can see here that those and those are similar. So those pairs that are coincident, we have done a manually validation later. So to check those matches, as I said, we have used those Euclidean maps that show which of the 20 newly computed clusters match with the old 40 clusters. So we can see some examples of those matches. No, previously, what we are going to see here is the final result of this matching process. So this is a distribution in terms of percentage of the time series of the pre and post data sets among the selected clusters. So we can see, for example, that 17 of the 20 generated clusters in the pre-COVID load profiles have been found in the previously 40 clusters, whereas 19 of the 20 generated clusters have a match. So the missing clusters, such as, for example, 9 or 15 or 25, the missing clusters only represent less than 2% of the total data set, so they are not relevant in this outcome. So we can see a bit of this comparison after analyzing visually the heat maps generated by each of the new clusters. We can identify some indicators of the lockdowns in Spain. For example, this is here we can see the first in this pattern. We can see clearly here that during the lockdown, the consumption is more intense throughout the day, and also we can see how mobility restrictions that there was another regional lockdown at the end of the year. Those mobility restrictions also affected the first days of December, which in Spain is a period which usually has bank holidays. So probably this is clearly better seen in this pattern here. Those are the same pattern, but in this case, this is the pre-COVID situation, and here is the post-COVID situation, in which we can see that the energy is more intense during the in-home lockdown and also during the regional. Just to conclude, some of the tasks that remain to be done are those ones. For example, computing new features that show time series or how the time series correlate with the weather or with the socio-economical indicators, or building some forecasting methods that are able to determine the consumption pattern for a socio-economic profile and obtain the other way around, vice versa. So this would be next steps, and with those next steps, I conclude my presentation. Thank you very much, and I will be attending for your questions, or I don't know if we have to ask questions here or later in the subsequent panel that we have before. Thank you very much.
Thank you very much, Carlos. As you have managed quite well the time, I think that we have some time for questions.
Great.
So I don't know if anyone have any question for Carlos. Please don't be shy. You can put in the chat, or you mute yourself and ask directly to Carlos.
Chris Mervey.
Hi, Carlos. Yeah, it's Chris here.
Hi, Chris.
Hi. Excellent presentation. I mean, I've heard many of these things before, but I like the way you presented everything, and I've understood even more now that you've explained it for the third time, probably. Can we go back to the heat map where the post-COVID, pre-COVID, so with the Yeah, one more back, I think.
This one?
No, still a bit more.
This
This one. Yeah, I
Yeah.
didn't understand this one. Could you please explain? So
Yeah.
we have on the vertical axis 20 clusters, but there are
Yes.
20 clusters plus another 20 clusters. And what do the
No.
colors mean? I didn't get that.
I mean, yeah. Here, what we are comparing are the 20 pre-COVID clusters first, and then in another image like this, the 20 post clusters. So when we are comparing, we are selecting just the pre or the post, and we are comparing those 20. What we are doing is measuring the distances between those 20 that are the newly computed with the 40 that we had computed before. Okay, so we have measured the distance between one cluster and another cluster. So the intensity of the color is showing to you that that's a match. I mean, that the distance is the shortest distance. So, for example, in that case, the cluster number 1 of the 20 pre-COVID clusters matches a lot with the cluster number 20 of the top 20, the top 40 clusters. So we say that the cluster number 1 of the 20 pre-COVID cluster matches with the cluster number 20 of the top 40. So this is the meaning of this. So as you can see, for example, there are places or there are clusters of the 40 clustering in which the intensity appears the same for different clusters of the 20 pre-COVID pre-computed of the 20 pre-COVID clusters. So in those cases, we have selected the match of the most intense one, and the others have been matched manually, let's say, but using those intensity of color. So if it doesn't matches with the first most intense, we go to the second most intense, and that's the way in which we have done that matching. And doing that matching has allowed us to obtain this parallelism between the pre-COVID and the post-COVID. I hope you have understood perfectly the...
Yes, now I do, because I thought that this graph had both the pre and the post, but it's not. It's either the pre or the post. Yeah,
that's
I see.
Thing. One for the first, one for the pre, and another for the post.
And the columns like column 22 and 36, for example, they're all clear. There is no. That means there is no match, no corresponding cluster found in.
They are clusters in the top 40 clustering that we have performed that don't have any equivalence with the pre and post 20 computed, which is normal, because I mean we are doing a matching with less quantity or amount of clusters than the ones that we have.
Exactly. Yeah. Okay. Thank you very much. That's perfectly understood now.
You're welcome.